A system of linear equations is just a set of equations for lines that we look at the same time. What we're interested in is whether those lines have any points in common. One way to find that out is to just graph the two lines. If we can find a point that the two lines have in common, that point is called the solution to the system of linear equations. These lines cross at the point 4, 1. So the solution to the system is x equals 4 and y equals 1. That also means that if we substitute 4 for x and 1 for y in both equations, we'll get a true statement for each equation. While graphing both lines can give us a really good visual representation of what the solution means, it's not always the most efficient way to find the solution. So let's think about how we might want to find the solution to this same system of equations without graphing. One alternative to graphing is to use a method called solving by elimination. Here's the idea behind elimination. When we look at an equation, we can think of it like a balance scale. Sometimes when we look at an equation, we say that it's balanced. And what we mean is that the two sides of the equation have the same value, kind of like having the same weight. So if we put the left side in one pan of our scale and the right side in the other pan, the scale will still balance. Now let's do the same thing with the other equation. Now if we look to see what's inside each pan, we may notice that we can do some simplification. In the right pan we have 3 and 5, and those combine to give us 8. And on the left pan, we've got negative y and positive y. Well, those are opposites, so they add together to give us 0. And that's where elimination gets its name. What we've done is eliminated the y variable by combining the two equations. That's the reasoning behind solving a system of equations by elimination. So let's do that with these two equations. First of all, let's just rearrange the two equations so that the left sides and the right sides align vertically. What we're going to do is add what we see on the left sides of the equal sign together. In essence, it's like putting them in the same pan and then combining whatever we see that's a like term. And we do see something that's a like term on the left side. We see a positive y and a negative y, and those do add to give us 0 since they're opposites. We also see x plus x on the left side, and those add to give us 2x. And on the right side of the equal sign, well, 5 plus 3, that's 8. Now that we've eliminated the y variable, we've got an equation with only one variable in it, and that's the x. So we can solve for that remaining variable. We'll just divide both sides by 2, and we get x equals 4. Now that's only half of our solution. Remember, we're finding a number for x and a number for y, an ordered pair that represents the point that these two lines have in common. So to find the other variable's value, to find the y's value, we can take either equation we started with and substitute the 4 in for the x. And now that we've done that, we can solve for the y by subtracting 4 from each side and then dividing both sides of the equation by -1. And now we know what the y value is for our solution. Y equals 1. Now to confirm that we found that solution, we could substitute 4 for x and 1 for y in both of the equations to make sure that we get a true statement for each one. And that's how solving by elimination works. The key is, can you find a variable that has opposite coefficients so that when you add, that variable will be eliminated? Now let's look at one more example. Here's a set of linear equations, and what we're going to try to do is add them together to eliminate a variable. So let's see what we have to begin with. Well, if we added right now, we wouldn't be able to eliminate the x variables because their coefficients are not opposites. And we wouldn't be able to eliminate the y variables either because their coefficients are not opposites either, although they do have opposite signs. So let's rewrite one of these equations so that when we add them together, we can eliminate those y's. What we can do is multiply both sides of that first equation by 2. When we do that, we still have an equation that represents the same line, but we've just doubled all of the terms in the equation. Now, if we add that new version of the first equation to the second equation, we can see that the y variables do have opposite coefficients, and they will add to give us 0. The 6x and the 2x will add to give us 8x, and on the right side of the equal sign, the 8 and the 1 add to give us 9. And now all we have to do is divide both sides by 8 to get the solution for our x-coordinate of our point of intersection. But we still need to get the y-coordinate. We'll take one of our two equations. It doesn't matter which one. We'll substitute 9/8 for x, and then we'll solve for y. When we do that, we do have a lot of work to do with fractions, and we end up with y equals 5/16. But we still have our solution. X equals 9/8, y equals 5/16. So 9/8, 5/16 is the point of intersection for the two lines. Now, not everybody likes working with those fractions to get that second coordinate. So let's talk about another way we could get that 5/16 once we've got x equals 9/8. When we added the two equations together, we eliminated the y's because the coefficients of the y's were opposites, 4 and -4. But maybe what we can do is try to eliminate the x's now. And in order to do that, we need to have the x coefficients opposites as well. We can do that if we multiply the second equation by -3 on both sides. And now we can see that the x coordinates are opposites, 6 and -6. So when we add these equations together, we get 16y equals 5, and it's pretty easy to get y equals 5/16 from there. So you may find that to be a little bit easier to do if you have fractions for any of your solutions as you're solving the problem.